we present dynamic layer detection of thin materials using DenseTact Optical Tactile sensors. Interacting with thin, deformable materials is required for many everyday tasks. For example, handling cloth while folding clothes or making the bed, and handling paper while turning pages or opening documents. However, these materials are challenging for robots due to having complex dynamics, high degrees of freedom, and self-occlusions. As a result of these challenges, these materials often become folded or bunched up during manipulation. Thus, it's important that robots are able to identify how many layers of material are grasped to effectively perform many tasks. To address this problem, we developed a custom gripper equipped with DenseTact Optical Tactile sensors. To detect the number of grasped layers, the gripper executes a dynamic rubbing motion and uses the collected tactile information in a transformer-based network. This video shows one trial of data collection with the cloth material. The gripper features a compact design using 4 Dynamixel motors and DenseTact 2.0 optical tactile sensors as fingertips. After grasping the cloth, the gripper performs the pre-programmed rubbing motion shown. The DenseTact's RGB camera feed and 6-axis wrench estimation are recorded for the duration of the motion, along with the joint states of the gripper. The RGB videos are used to calculate optical flow, and the collected sequences of optical flow, 6-axis wrench, and joint state data are used to identify whether 0, 1, 2, or 3 layers were grasped. Using this cloth, 92 trials were collected for each of these 4 classes, for a total of 368 trials of data. Here is the architecture of our classifier model. As mentioned, the model takes the optical flow, 6-axis wrench, and joint state data sequences as inputs. Each input goes through a feature extractor to capture notable patterns that differentiate between classes. All extracted features are then concatenated and fed into a transformer encoder, which uses attention mechanisms to understand feature time dependence in the data. This is especially suited to our method as our input data are time sequences collected during the rubbing motion. A softmax function is used to obtain a probability distribution across the 4 classes. The class with the highest probability is taken as the predicted number of layers. This video shows our method working in real time. The input data is fed into our model as it is being collected, allowing us to classify the number of layers while the material is being rubbed. Here, it takes roughly 2 rubs back and forth to identify that 2 layers are being grasped. Our method achieved a test accuracy of 98% for the cloth material. This confusion matrix shows the classification results for the 56 test trials, where only 1 was misclassified. To evaluate our method's performance on other thin materials, we also performed the task on standard printer paper. Data was obtained using the same process, with 50 trials collected for each class in total. When trained and tested with this paper data, our method achieved a test accuracy of 81%. This lower accuracy is because multiple layers of paper are much harder to differentiate between than with cloth. Overall, our results show that using a dynamic rubbing motion, tactile sensor information, and a transformer-based model is extremely effective for cloth layer classification and promising for even more difficult materials such as paper.